In this video, what we're going to have a look at is we're going to have a look at solving exponential equations. Now we will get to a stage with an exponential equation. Remember, that's something to the power of the variable. So you'll see shortly. I mean, it could be something like, 3 to the power x. If I said that equals 2, what does x have to be? Okay, that is what we'd call an exponential equation. We need to use logs to solve this sort of thing. We'll be doing a few examples in a minute. Now, on your calculator, there are two sorts of commonly available logs. There's one which they just call log. If you look at your calculator, you'll see there's a button with log on it. That means log to the base 10. Okay? The other one is line. You'll see that one there. Now, line is log to the base e. E is a special number. It's an irrational number, a bit like pi. It's about 2.7. There are lots of properties about this number, but they're beyond basically what's involved on the higher course. If you go on to do advanced higher, you will see that E comes into it a bit more there, and we'll go into that a bit more then. But if we're looking at E, it's about 2.7. It's an irrational number. So sometimes you might have an equation of the form e to the x, or some number x, say you had e to the, let's make it 5x, is equal to, say I said 300. That would be one where, yes, we'd use logs, but because it's based on this number e, yeah, okay, we'd be using the natural log with these. So we have the special number e. As I said, it's a bit like pi, but it's one we use quite a lot. Okay, the opposite of that is line. It's pronounced line, ln, on your calculator, and it's log to the base e. The other sort we have is, that's easily available on your calculator, is log. Actually stands for log to the base 10. Okay, so we tend to use one of these two to solve these sorts of equations, okay? What we call an exponential equation. We'll go on and do a few examples that will make a bit more sense then. Okay, let's have a wee look at first question here. Look, it's an exponential equation. Look, it's a constant to the power x. So we're working out the power here. Now, if I looked at that, okay, then I could use log to the base e or log to the base 10. I'm going to use log to the base 10 for it, because if I take the log of both sides here, yeah, we'd get that, wouldn't we? But if you remember from the rules of logs, when we take the log, the power becomes the multiplier at the start. So that means x log to the base 10 of 5 equals log to the base 10 of 32. So x is log to the base 10 of 32 divided by log to the base 10 of 5. And that I can do on my calculator. Bring my calculator, turn it on. Log is that button there. So if we looked at it, it's going to be, and we know our fraction button's there, so fraction. Log stands for log to the base 10. Remember I said that in the last bit, of 32. Close the bracket. Go on to the bottom line, divided by log of 5 equals. I'm working that out. It's got 2.15 to 2 decimal places. So that gives me 2.1522 decimal places. Up till now, before we learnt about logs, the only way of solving something like this would have been a trial and improvement method, which would have taken a long time, but this takes us straight to an answer. Okay, the next one's set in context. Look, at 2% per annum per year, how long would it take £100 to get up to £180? Well, remember, it's going to be 100 plus 2, 102% of what you started with. So your multiplier is 1.02 to the number of years. Let's call the number of years x. So what we've got is 100 times 1.02 power x equals 180, doesn't it? Yeah? Because it's 2% per annum, so you're multiplying each year by 1.02, but it's the number of years we want to work out, so it's the power we wanted to work out. So first of all here, let's divide by 100. So we've got 1.02 to the power x equals 1.8. Now it's exactly the same sort of problem we had over here. Now I can use log to the base e, or I could use log to the base 10. Because we used log to the base 10 last time, let's use log to the base e this time. So, again, if I take line of both sides, we're going to have line 1.02. Remember, it would have been to the power x. The power, remember, becomes the multiplier. Line of 1.8. So, x will be line of 1.8 divided by line of 1.02. Remember, line's just log to the base e. Okay, so this time, fraction button, we wanted line, which is that one on your calculator. So line 1.8 over line 1.02. And if we work that out, it tells me 29.68. So let's just say that's about 29.7 years. So that's how long it would take at 2% interest for your deposit account to go from £100 to £180. Nearly 30 years. Okay, so that's two examples. We're going to do another one in a minute, and then we've got two more examples, both of which will be set in context. Okay, let's have a look at a typical growth one. Something that grows exponentially. Could be something like a bacteria population. So a bacteria is known to multiply in a pie according to the formula P of t equals 100,000 e to the power 0.5 t, where t is the time in hours after the pie leaves the oven. Okay, first bit says, what is the initial population? Okay, initial just means t equals 0. So, P of 0 is going to be 100,000. Now, that is e to the power 0. Remember, e is this special number. But anything to the power 0 is just 1. So that's just 100,000. Yeah? So when t equals 0, that is 1. So it's 100,000. Okay? That's a standard sort of 1 mark question at the start of one of these. Next thing it says, the bacteria is known to be harmful when it reaches a population of 4 million. How long after leaving the oven does this happen? Now, that gives me 4 million, yeah, equals this thing, which is 100,000 e to the power 0.5 t. That's our exponential equation. Okay? Because it was 4 million. That's when there is too much bacteria in this pie. Therefore, it shouldn't be eaten. It should be thrown away. It's become a dodgy pie. So, 4 million divided by 100,000 would give me 40. So, simplifying that, we've got e to the power 0.5t equals 40. Now, because it's e, I would probably use line. I'll show you using log to the base 10 as well later. But it's just line makes the arithmetic a little bit easier. Because remember, line is log to the base e, and log to the base e of e to the power 0.5 is just 0.5, yeah? Remember, log to the base e to the power 0.5t, same as log to the base e, which is line of 40. Remember, log to the base e, on your calculator it's written as line. Okay? So if we do that and that cancel each other out, just leaving you 0.5t equals log to the base e of 40. So t would be log to the base e, or line, of 40 divided by 0.5. And if we work that out, log, turn it on, that would help, log to the base e, line, of 40 divided by 0.5 gives me 7.37, which I'll round to 7.4 hours. That's when you should throw the pie away because there's too many bacteria in it for it to be safe to eat. I'll do this last stage here. It wouldn't make any difference if I did log to the base 10. It's just if we do that, that's going to give me the power, remember, goes to the front. So 0.5t log to the base 10 would be the same as log to the base 10 of 40 divided by log to the base 10 of e. Okay, you can do that on your calculator if you want. If you do shift and then the line button, then it gives you e. Okay, and therefore t would be exactly the same, 7.4 hours. But it's a little bit more complicated doing it that way. So that's, as I said, why, if it's in terms of e, I would tend to use line, log to the base e. Okay, so either way it would work, but I think if it's in terms of e, you make life a bit simpler for yourself if you use line, log to the base e. Okay, in this final example, we're looking at something called half-life. Half-life is the time something takes to drop to half of what it originally contained. Okay, there's a number of things. It's quite often used with nuclear materials and so on. But in this case, we're looking at the concentration of liquid fertilizer, supergrow, in the soil is given by this. Now we've got C, so it's the concentration in terms of time, so that's CT, is equal to the original concentration, C0 means the concentration at the start, times e to the power minus KT. So C0 and K are constants. It's a minus because it's a decay function. It's getting less. Okay, so if it's a decay function, that's always going to be a minus bit up here, or the number that you're raising to the power would have to be less than 1. It's one of those two. In this case, because it's E, which you know is this special number, about 2.7, okay, then, yeah, it's going to be a minus up there. But they've told us the half-life of supergrow is 5 days. So the concentration after 5 days is half of what you started with, which was C0. Okay, And that, remember, is equal to this thing, which is C naught E. Now remember we said T is 5, so minus 5k. Okay, we can divide by C naught here, so half equals E to the minus 5k there. Remember, the opposite of e to the power is line, which remember is log to the base e. So we want to get back to the original bit. So what we can write down is line of a half, remember that's log to the base e, is equal to minus 5k. Okay? And if we work that out, you'd need to use your calculator for this with the line button on it. That is, line of a half is about 0.139. Okay, so our equation is C of t equals C naught e to the power minus 0.139 t. Okay, we worked it out to 3 decimal places. So that's our equation. Then they asked 2 weeks after application. Well, 2 weeks means that it's 14 days, so t is 14, because remember t is the time in days after the original application. Okay, so we want C of 14. If I put that into this thing here, that's C naught, the original amount, times e to the minus 0.139 times 14. If you work out this bit, the e to the power, yeah, using your calculator, okay, so you use your calculator to work out e to that power there, and that should give you 0.1428 roughly C naught, okay, because that bit there gives you that when you do it on your calculator. Now that means we've got, that's a decimal, so we've got about, what, 14.3% of what we started with. So of the original concentration. So that would be a tricky question involving log equations. You should now be able to have a go at the questions.